If you're watching on a smaller screen, consider going full screen for the complete experience. And if this journey resonates with you, subscribing helps us continue exploring these deep questions. Now, let us turn our attention outward, beyond the blue envelope of our own world, to a place where the sky itself has become a furnace and the ground glows with the memory of heat that never fades. Venus hangs in the black. It is the second stone from the sun, a world almost precisely the size of Earth, almost precisely the same mass, formed from the same swirling disk of dust and gas that gave birth to our own planet 4.5 billion years ago. In size, in composition, in the fundamental architecture of rock and metal, Venus is Earth's twin. Yet to call them twins is to invoke only the most superficial resemblance, the kind that disappears the moment you look closer. Venus is not a mirror of Earth. It is a warning written in carbon dioxide and sulfuric acid, a cautionary tale inscribed across an entire planet, a world that might once have been something altogether different, something gentler, something capable of cradling the fragile chemistry we call life, and then lost it all. To understand what Venus might have been, we must first confront what Venus is now. The planet rotates slowly, so slowly that a single day on Venus lasts longer than a Venusian year. It spins backward relative to most other planets, its sun rising in the west and setting in the east, a ponderous clockwise rotation when viewed from above the solar system's north pole, moving in the opposite direction of its orbit around the sun. The reasons for this retrograde spin remain unclear, though theories abound. Perhaps a massive impact early in the planet's history knocked it askew. Perhaps the thick atmosphere itself, through tidal forces and friction over billions of years, gradually slowed and reversed the planet's rotation. Whatever the cause, Venus now turns with a kind of stubborn defiance, taking 243 Earth days to complete a single rotation, while completing its solar orbit in only 225 days. The surface pressure at the base of the Venusian atmosphere exceeds 90 Earth atmospheres, equivalent to the pressure experienced a kilometer beneath Earth's oceans. This is not merely uncomfortable. This is crushing. Spacecraft that have landed on Venus have survived only minutes before being compressed and cooked into silence. The atmosphere itself is almost entirely carbon dioxide, with thick clouds of sulfuric acid droplets swirling at altitudes between 40 and 70 kilometers. These clouds are not the white, cottony structures we see from Earth's surface. They are dense, opaque, yellowish layers that completely obscure the surface from external view, reflecting most incoming sunlight back into space and giving Venus its brilliant appearance in our sky. Yet, despite this high reflectivity, the surface temperature remains locked at around 467 degrees Celsius, hot enough to melt lead, hot enough to glow faintly in the darkness. This infernal heat is not primarily the result of Venus's proximity to the Sun. Venus receives about twice the solar energy per square meter that Earth does, but this alone cannot account for the extreme surface temperatures. The true culprit is the greenhouse effect, operating here at a scale and intensity unmatched anywhere else in the solar system. The thick carbon dioxide atmosphere traps infrared radiation attempting to escape from the surface. Photons emitted by the hot ground are absorbed by carbon dioxide molecules, which then re-emit them in random directions, many back toward the surface. This radiation is absorbed again, re-emitted again, creating a cascade of energy trapping that drives surface temperatures far higher than the sun's input alone would suggest. The sulfuric acid clouds play their role as well, absorbing and scattering infrared radiation, adding additional layers to the thermal blanket smothering the planet. The surface itself is a landscape of volcanic plains, highland plateaus, and vast lava flows frozen in time. Radar mapping from orbit has revealed a world shaped primarily by volcanism. Enormous shield volcanoes rise from the plains, some larger than any on Earth. Vast corona structures, circular or elliptical features hundreds of kilometers across, mark places where mantle plumes have pushed upward against the crust. Lava channels extend for thousands of kilometers, carved by flowing molten rock more fluid than Earth's basaltic lavas, possibly enriched in minerals that lower the melting point and viscosity. There are impact craters scattered across the surface, but surprisingly few, and none smaller than a few kilometers in diameter. The thick atmosphere incinerates smaller meteoroids before they reach the ground, and the relative youth of the surface, perhaps only a few 100 million years old, suggests that volcanic resurfacing has erased older craters, though whether this resurfacing happened gradually or in a single catastrophic episode remains debated. The rocks themselves are basaltic, similar to Earth's oceanic crust and volcanic islands. Soviet Venera landers, those remarkable machines that parachuted through the acid clouds and transmitted data from the surface for brief minutes before succumbing to heat and pressure, analyzed the composition of the soil and found it consistent with volcanic origin. The landscape they photographed showed flat expanses of broken rock, slabs of stone fractured by thermal stress, resting under a dim orange sky. The light reaching the surface is filtered through so many kilometers of dense atmosphere that it arrives diffused and tinted, casting no sharp shadows, creating a world of uniform illumination without contrast, without relief, a place where distance and perspective become difficult to judge. There is no water on the surface of Venus. None. The temperatures are far too high for liquid water to exist at any pressure. Any water molecule present in the atmosphere is rapidly broken apart by ultraviolet light from the sun, split into hydrogen and oxygen. The hydrogen, being light, escapes to space. The oxygen reacts with surface rocks or with sulfur compounds in the atmosphere. This process, continued over geological time, has stripped Venus of whatever water it once possessed. Measurements of the hydrogen isotope ratio in Venus's atmosphere reveal an excess of deuterium relative to normal hydrogen, a signature of preferential loss. Lighter hydrogen escapes more easily than its heavier isotope, so over time the remaining hydrogen becomes enriched in deuterium. The ratio observed in Venus's atmosphere suggests that the planet once had significantly more water than it does now, perhaps even enough to form oceans, though how much water and for how long remain open questions. This is the Venus we observe today, a world of blistering heat, crushing pressure, corrosive clouds, and utter desiccation. It is a world hostile to any form of life we know. Yet the question that drives this inquiry is not about the Venus of today, but about the Venus of the deep past, the Venus of 4 billion years ago, or 3.5 billion, or even 3 billion. The question is whether this hellish planet was always hell, or whether it began as something else, something more temperate, something more like the early Earth, and if so, whether life might have taken root there in that ancient, vanished world. To approach this question, we must travel backward in time, not through speculation alone, but through the application of planetary science, climate modeling, and an understanding of how stars and planets evolve. We must consider the young sun, the processes that shaped planetary atmospheres, the role of water and carbon dioxide in regulating surface temperatures, and the mechanisms by which a planet can transition from habitability to sterility. 4.5 billion years ago, the sun was newly born, a young star emerging from the gravitational collapse of a molecular cloud. Young stars are dimmer than mature stars of the same mass. The sun, in its infancy, emitted only about 70% of the light it produces today. This phenomenon, known as the faint young sun problem, has profound implications for the early climates of the inner planets. With less solar energy reaching Earth and Venus, both planets should have been frozen worlds, their surfaces locked beneath ice, incapable of supporting liquid water. Yet evidence from Earth's geological record shows that liquid water existed on Earth's surface as far back as 4 billion years ago, perhaps even earlier. Ancient zircon crystals from Western Australia, dated to over 4 billion years in age, contain oxygen isotope ratios that suggest they formed in the presence of liquid water. Sedimentary rocks from the Archean eon, spanning from 4 to 2.5 billion years ago, show features consistent with deposition in aquatic environments. The resolution to the faint young sun problem lies in greenhouse warming. Earth's early atmosphere was different from today's, likely rich in carbon dioxide and perhaps methane, gases that trap infrared radiation and warm the surface even when solar input is low. The balance between incoming solar energy, atmospheric composition, and surface temperature is delicate, mediated by feedbacks that can amplify or dampen changes. On Earth, the carbon cycle plays a stabilizing role. Carbon dioxide dissolves in rainwater to form carbonic acid, which weathers silicate rocks, releasing calcium and magnesium ions that eventually wash into the ocean. Characterizing the atmospheres of these planets, searching for gases like oxygen, methane, or phosphine that might indicate life, is a major goal of current and future telescopes. The James Webb Space Telescope, launched in 2021, is beginning to observe exoplanet atmospheres in unprecedented detail, though detecting definitive biosignatures remains challenging. Future telescopes, larger and more sensitive, will continue this work, building a statistical picture of how common habitable planets are and whether life is rare or abundant in the galaxy. Venus fits into this larger picture as a cautionary tale and a test case. If Venus was once habitable and lost that habitability, it demonstrates that planets can transition from life-supporting to life-extinguishing. This is relevant for understanding exoplanets. Many of the rocky planets discovered around other stars are closer to their suns than Earth is to ours, receiving more intense radiation, and thus more likely to be in a Venus-like state than an Earth-like state. Understanding the conditions under which a planet becomes a Venus rather than an Earth helps us assess the habitability of exoplanets and refine our search strategies. Moreover, Venus provides an opportunity to study the end state of a runaway greenhouse, to see in detail what happens when climate feedback loops spiral out of control. This has implications for Earth. While Earth is not in immediate danger of becoming Venus, the ongoing increase in carbon dioxide due to human activities is raising global temperatures, melting ice, shifting weather patterns, and acidifying oceans. Understanding the mechanisms that drive extreme climate change on Venus can inform our understanding of Earth's climate system, highlighting which feedbacks are most dangerous and what thresholds we should avoid crossing. The study of planetary climate is inherently comparative. No planet is an island. Each world we study provides data points, examples of how physics, chemistry, and geology interact to create climates. Earth is our only example of a continuously habitable planet, but Mars, Venus, Titan, and the exoplanets provide contrasts, showing what happens under different conditions. By studying Venus's history and current state, we learn not just about Venus but about the general principles governing planetary habitability. Returning to the question of early Venus, the evidence is circumstantial but suggestive. The deuterium enrichment indicates substantial water loss, implying that Venus once had more water than it does now. Climate models show that, under certain assumptions, early Venus could have maintained liquid water on its surface for hundreds of millions to a few billion years, depending on initial water content, cloud properties, and the evolution of solar luminosity. The geological record, such as it is, shows a planet dominated by volcanism, but with few features that can be definitively dated to the first billion years. The surface we see today is relatively young, shaped by processes that occurred long after any habitable period would have ended. There are tantalizing hints in the atmospheric composition. Venus's atmosphere contains trace amounts of water vapor, a few tens of parts per million, enough to measure but far less than the saturated steam atmosphere that would have existed during the runaway greenhouse. There are also trace gases like sulfur dioxide, carbon monoxide, and hydrogen sulfide, products of volcanic outgassing and atmospheric chemistry. The ratios of isotopes in these gases, particularly the ratios of noble gas isotopes like argon and neon, provide clues about the planet's formation and the loss of its atmosphere over time. Argon-36, a light isotope, is depleted relative to argon-38, a heavier isotope, suggesting preferential loss of the lighter isotope, consistent with atmospheric erosion by the solar wind. Neon isotopes show similar patterns. These measurements, while technical, help constrain models of atmospheric evolution and the timing of water loss. Another piece of the puzzle comes from the study of Venus's surface mineralogy. Although we have not sampled many locations directly, radar observations from orbit can distinguish between different rock types based on their reflectivity and surface roughness. Some highland regions on Venus have high radar reflectivity, suggesting the presence of minerals that form under cooler, wetter conditions than currently exist. One hypothesis is that these are weathering products, such as iron pyrite or other sulfide minerals that form when volcanic rocks interact with sulfur-rich gases in the atmosphere. However, another hypothesis is that these minerals are remnants from an earlier, wetter era, when liquid water was present. Distinguishing between these interpretations requires better data, ideally from landers that can analyze the rocks directly. The sky might have been overcast, thick clouds reflecting much of the incoming sunlight, keeping surface conditions dim and diffuse, but not dark. Rain would have fallen, perhaps more sporadically than on Earth, perhaps in intense episodes driven by convection in the hot, moisture-laden atmosphere. Rivers would have carved channels across the land, if land existed above the waterline, delivering sediments and dissolved minerals to the seas. In such an environment, the chemistry necessary for life could have operated. Liquid water is essential, serving as a solvent that enables complex molecules to interact, react, and organize. The building blocks of life, amino acids and nucleotides and lipids, can form through abiotic processes in hydrothermal environments, in tidal pools, or even delivered by meteorites. Volcanic activity on early Venus would have provided heat and chemical gradients, creating niches where energy could be harvested by primitive metabolisms. Hydrothermal vents on the seafloor, if Venus had seas and seafloors, could have been sites of chemical synthesis and early biological innovation, just as they may have been on Earth. Life on Earth is tenacious, adaptable, capable of colonizing environments that seem impossibly hostile. Microorganisms thrive in boiling hot springs, in acidic mine drainage, in the deep subsurface kilometers below the surface, in hypersaline lakes, and beneath Antarctic ice. Thermophilic bacteria and archaea flourish in temperatures exceeding 100 degrees Celsius. Acidophiles live in solutions with pH values below 1. Halophiles survive in saturated brines. This adaptability suggests that life, once established, can tolerate a wide range of conditions. If life arose on early Venus, it might have been thermophilic from the outset, adapted to the warm seas and hot volcanic environments. It might have been chemolithotrophic, deriving energy from the oxidation of sulfur or iron or hydrogen, independent of sunlight. Or it might have been photosynthetic, harnessing the dim light filtering through the clouds, though photosynthesis is a relatively complex metabolic pathway that may have taken longer to evolve. The critical question is not whether life could have survived on early Venus, but whether the conditions remained stable long enough for life to originate and establish itself. The origin of life is not instantaneous. It requires the accumulation of organic molecules, the formation of self-replicating systems, the emergence of metabolism, and the development of cellular structures that separate the internal chemistry of life from the external environment. On Earth, this process may have taken tens or hundreds of millions of years. If Venus's habitable window was short, measured in a few 100 million years or less, the timing becomes tight. Life would have had to originate quickly and then cope with a rapidly deteriorating environment. The transition from habitable Venus to the Venus we see today was driven by the interplay of solar luminosity, atmospheric composition, and geological processes. As the Sun aged and brightened, Venus received more energy. The increased solar heating raised surface temperatures, enhancing evaporation and increasing the atmospheric water vapor content. More water vapor meant stronger greenhouse warming, which raised temperatures further, creating the positive feedback loop that leads to a runaway greenhouse. Once initiated, this process is difficult to stop. The atmosphere becomes increasingly opaque to infrared radiation, trapping more and more heat until the oceans evaporate completely. The loss of oceans has profound consequences. Without liquid water on the surface, the carbon cycle shuts down. On Earth, carbon dioxide is removed from the atmosphere through weathering and precipitation of carbonates, processes that require liquid water. On a waterless Venus, carbon dioxide released by volcanic activity accumulates in the atmosphere with no removal mechanism. Over time, the atmospheric carbon dioxide content increases, strengthening the greenhouse effect even further. The surface temperature rises to the point where even the upper atmospheric layers become too hot to allow infrared radiation to escape efficiently. The planet settles into a new equilibrium, a scorching, high-pressure state from which there is no return. Photodissociation of water vapor in the upper atmosphere proceeds continuously as long as ultraviolet light from the sun is available. Water molecules are split into hydrogen and oxygen. The hydrogen, being the lightest element, is moving fast enough at the temperatures of the upper atmosphere that a significant fraction exceeds escape velocity and is lost to space. Oxygen, being heavier, does not escape as easily. Initially, the oxygen accumulates in the atmosphere, but it is highly reactive. It oxidizes surface rocks, combining with iron and sulfur and other elements, becoming locked into minerals. Some oxygen may be lost through non-thermal escape processes, such as being picked up by the solar wind or through chemical reactions at the top of the atmosphere. Over hundreds of millions of years, the combination of hydrogen escape and oxygen sequestration strips the planet of its water. The deuterium enrichment observed in Venus's atmosphere today provides a measure of how much water was lost. Deuterium is an isotope of hydrogen with 1 proton and 1 neutron, making it roughly twice as heavy as ordinary hydrogen. When hydrogen escapes to space, the lighter isotope preferentially escapes, leaving the remaining hydrogen enriched in deuterium. The ratio of deuterium to hydrogen in Venus's atmosphere is about 150 times higher than the ratio in Earth's oceans. If we assume that Venus started with a deuterium to hydrogen ratio similar to Earth's, this enrichment implies that Venus lost an enormous amount of hydrogen, equivalent to an ocean covering the entire planet to a depth of several meters at minimum, and possibly much more, depending on how much oxygen was sequestered in rocks versus lost to space. Several meters of water distributed evenly over Venus's surface is not a large ocean by Earth's standards, but it is significant. Earth's oceans, if spread evenly, would cover the planet to a depth of about 2.7 kilometers. Venus might never have had oceans that deep, but it could have had shallow seas, large lakes, or a humid atmosphere with periodic rain and surface water accumulation. Alternatively, much of Venus's initial water inventory might have been lost even before oceans could form, if the planet was born hot and the runaway greenhouse initiated very early. Disentangling these scenarios requires better understanding of planetary formation and the delivery of volatiles to the inner solar system. Water and other volatiles could have been delivered to Venus through several mechanisms. During the late stages of planetary accretion, after the major planets had formed, the inner solar system was bombarded by asteroids and comets, remnants of the protoplanetary disk. Comets, originating in the cold outer reaches of the solar system, are rich in water ice. Asteroids, depending on their composition and formation location, can also contain significant amounts of water, either as ice or bound in hydrated minerals. Impacts from these bodies would have delivered water and organic molecules to the surfaces of the terrestrial planets. Earth likely received much of its water this way, during a period known as the Late Heavy Bombardment, which occurred around 4 billion years ago. Venus, being closer to the Sun, would have received impacts from objects with somewhat different compositions, possibly with less water on average due to the higher temperatures in the inner solar system, but still substantial amounts could have accumulated. The timing and magnitude of water delivery to Venus depend on the dynamics of the early solar system, which in turn depend on the migration of the giant planets. Jupiter and Saturn, through their gravitational interactions, may have migrated inward and then outward during the solar system's youth, a scenario known as the Grand Tack hypothesis. This migration would have stirred up the asteroid belt, flinging water-rich bodies inward toward the terrestrial planets. If this occurred, Venus could have received a significant influx of water, potentially enough to form oceans. However, if Venus was already too hot by the time this water arrived, it would have been lost almost immediately to photodissociation and escape, contributing only temporarily to a steam atmosphere. Another factor influencing Venus's habitability is the planet's lack of a strong magnetic field. Earth's magnetic field is generated by convection of molten iron in the outer core, a process driven by heat from the core and chemical differentiation. The magnetic field extends far into space, forming the magnetosphere, which deflects much of the solar wind, a stream of charged particles flowing from the Sun. Without this protection, the solar wind can interact directly with the upper atmosphere, stripping away ions and accelerating atmospheric loss. Venus lacks a significant intrinsic magnetic field, though it may have had one in the distant past. If Venus's core cooled and solidified, or if core convection ceased for some other reason, the magnetic field would have disappeared, leaving the atmosphere vulnerable to solar wind erosion. Over billions of years, this enhanced loss could have contributed to the removal of water and other volatiles. Mars provides a cautionary parallel. Mars is smaller than Earth and Venus, and its core cooled more rapidly. Mars lost its magnetic field early in its history, perhaps within the first few 100 million years. After the field disappeared, the solar wind began stripping away the Martian atmosphere, a process that continues today, measurable by spacecraft in orbit. Mars once had liquid water on its surface, evidenced by ancient river valleys, lake beds, and mineral deposits that form only in the presence of water. Yet today, Mars is cold, dry, and has an atmosphere less than 1% as thick as Earth's. The loss of the magnetic field, combined with Mars's weaker gravity, allowed the atmosphere to erode, lowering surface pressure and temperature until liquid water could no longer exist on the surface. Venus, with its greater mass and stronger gravity, retains a thick atmosphere despite lacking a magnetic field, but the loss of hydrogen to space would have been accelerated by solar wind interactions, hastening the planet's desiccation. Volcanism plays a dual role in planetary habitability. On one hand, volcanic outgassing replenishes the atmosphere, releasing water vapor, carbon dioxide, sulfur dioxide, and other gases from the planet's interior. On Earth, volcanism is essential for maintaining the carbon cycle, returning subducted carbon to the atmosphere and preventing the planet from freezing. On Venus, volcanism also releases gases, but without the carbon cycle to regulate carbon dioxide levels, volcanic outgassing leads to a runaway accumulation of greenhouse gases. The more volcanism, the more carbon dioxide, the hotter the surface, the more water is lost, creating a feedback that drives the planet toward its current state. The geological history of Venus is marked by extensive volcanism. Vast plains of basaltic lava cover much of the surface, and volcanic features dominate the landscape. However, the age of the surface is puzzling. Impact crater counts suggest that most of the surface is relatively young, around 500 to 700 million years old, give or take a few hundred million years. There are very few craters older than this, implying that some process erased the older cratering record. One hypothesis is that Venus experienced a global resurfacing event, a catastrophic episode during which volcanic activity covered the entire planet in fresh lava, burying or obliterating older features. Such an event could have been triggered by a buildup of heat in the mantle, perhaps because Venus lacks plate tectonics and thus lacks the efficient heat loss mechanism that tectonics provides. Heat accumulated until the lithosphere became unstable, broke apart, and was overwhelmed by massive volcanic eruptions. If Venus did undergo global resurfacing roughly 500 million years ago, this event would have been apocalyptic. Volcanic emissions would have injected enormous quantities of gases into the atmosphere, potentially altering its composition and opacity, changing surface temperatures and modifying the climate. However, by this time, Venus had long since lost its oceans, so the resurfacing would not have directly destroyed a habitable environment. Rather, it would have been a violent reorganization of a planet already in a runaway greenhouse state. Still, understanding this event is important for understanding Venus's thermal evolution and the longevity of any potential habitable period. Plate tectonics, the process by which Earth's lithosphere is broken into plates that move, collide, and subduct, is driven by mantle convection and facilitated by the presence of water. Water lowers the melting point of rocks and acts as a lubricant, making it easier for plates to slide past one another. Earth has plate tectonics, and this process is intimately connected to the planet's habitability. Subduction recycles surface materials into the mantle, regulating atmospheric composition and preventing the buildup of excessive greenhouse gases. Seafloor spreading at mid-ocean ridges creates new crust and provides sites for hydrothermal activity, which may have been crucial for the origin of life. Venus does not appear to have plate tectonics, at least not in the form seen on Earth. There are no obvious subduction zones, no mid-ocean ridges, no transform faults characteristic of moving plates. Instead, Venus's lithosphere may be a single, unbroken shell, or it may be broken into blocks that move only sluggishly. The lack of plate tectonics on Venus may be due to the absence of water. Without water to lubricate the lithosphere and weaken the rocks, the crust is too rigid to fracture and move in the way Earth's crust does. This creates a different mode of heat loss, one that may involve episodic catastrophic resurfacing rather than continuous, steady recycling. If early Venus had liquid water, it might also have had plate tectonics, at least temporarily. A wetter mantle and crust would have been more conducive to plate motion. If plate tectonics operated on early Venus, it would have provided a mechanism for regulating carbon dioxide, potentially extending the habitable period. However, as Venus lost its water, the lithosphere would have dried out, becoming more rigid, and plate tectonics would have ceased. The shutdown of tectonics would have disrupted the carbon cycle, allowing carbon dioxide to accumulate and hastening the transition to a runaway greenhouse. The interplay between water, tectonics, and climate on Venus is complex, involving feedbacks that operate on geological timescales. A planet's evolution is not deterministic, but contingent on initial conditions, timing, and the interplay of multiple processes. Small differences in starting conditions can lead to vastly different outcomes. Earth and Venus, despite their similarities in size and composition, followed divergent paths. Earth maintained liquid water, developed plate tectonics, and remained habitable for billions of years. Venus lost its water, possibly lost its tectonics, and became a hothouse. The question is whether this divergence was inevitable, or whether there were moments when Venus's fate hung in the balance, when different circumstances might have led to a different outcome. One key moment may have been the timing of water delivery. If Venus received its water early, before the sun brightened significantly, the planet might have been able to hold on to it longer, maintaining oceans and a stable climate. If water arrived later, after the planet had already heated up, it might have been lost quickly, never forming lasting seas. Another key moment may have been the development of life. On Earth, life profoundly altered the atmosphere. Photosynthetic organisms began producing oxygen around 2.5 billion years ago, during the Great Oxidation Event, fundamentally changing the planet's chemistry and climate. Life on Venus, if it existed, might have had similar effects, though the direction and magnitude of those effects would depend on the specifics of Venusian biochemistry and ecology. Microbial life can influence climate in several ways. Photosynthesis consumes carbon dioxide and releases oxygen, potentially drawing down greenhouse gases and cooling the planet. Methanogenesis, the production of methane by certain microbes, adds a potent greenhouse gas to the atmosphere, potentially warming the planet. Weathering rates can be enhanced by biological activity, as organisms break down rocks and accelerate the dissolution of minerals, affecting carbon dioxide removal. On Earth, the biosphere and the geosphere are deeply intertwined, with life shaping the environment and the environment shaping life. If Venus had a biosphere, even a simple one, it would have been part of the planet's climate system, and its fate would have been linked to the fate of the planet. Imagine a Venusian biosphere in the early oceans, communities of microbes clustered around hydrothermal vents, metabolizing sulfur and iron, building stromatolite-like structures in shallow coastal waters. Imagine photosynthetic mats floating on the surface of warm seas, tinted red or purple or green depending on the pigments they use to capture light. Imagine ecosystems adapted to the heat, thriving in water temperatures that would be lethal to most modern Earth organisms, but which were the norm on early Venus. These organisms would have been extremophiles by our standards, but on their own world, they would simply have been life, doing what life does, extracting energy from the environment, reproducing, evolving. As the sun brightened and Venus began to heat up, this biosphere would have faced increasing stress. Rising temperatures would have reduced the dissolved oxygen content of the water, making respiration more difficult. Evaporation would have concentrated salts and other solutes, increasing osmotic stress. The most vulnerable organisms would have died off first, shrinking the range of habitable niches. Populations would have retreated to refugia, cooler regions, deeper waters, places where conditions remained tolerable. But as the runaway greenhouse took hold, even these refugia would have become uninhabitable. The oceans would have warmed to the boiling point. Coastal waters would have evaporated first, then deeper basins, until the entire ocean was gone, injected into the atmosphere as steam. Could life have survived this transition? On Earth, life has survived multiple mass extinctions, events that killed the majority of species but left survivors that eventually radiated and repopulated the planet. The largest of these, the Permian-Triassic extinction, about 250 million years ago, killed over 90% of marine species and 70% of terrestrial species, yet life recovered. However, the environmental changes during that extinction, severe as they were, pale in comparison to the total evaporation of the oceans. The Permian-Triassic event involved volcanic eruptions, ocean anoxia, ocean acidification, rapid warming, and possibly hydrogen sulfide release, but liquid water remained. On Venus, the loss of liquid water would have been absolute, and with it, the loss of any environment where water-based life could function. There is a possibility, speculative but worth considering, that life could have retreated into the atmosphere. As the surface became uninhabitable, the clouds might have offered a refuge. At altitudes of 50 to 60 kilometers in Venus's current atmosphere, temperatures and pressures are relatively benign, roughly Earth-like. Temperatures range from 0 to 50 degrees Celsius, and pressures are around 1 Earth atmosphere. The clouds at these altitudes are composed of sulfuric acid droplets, which is problematic for most life, but not necessarily insurmountable. Some Earth microbes can tolerate acidic environments, and life is adaptable. If Venusian microbes could evolve acid resistance, or if they could encapsulate themselves in protective coatings, they might survive in the cloud layers, metabolizing sulfur compounds, floating on air currents, reproducing and dispersing as aerosols. This idea that Venus's clouds might harbor microbial life has gained traction in recent years following the controversial detection of phosphine in Venus's atmosphere. Phosphine, a molecule consisting of 1 phosphorus atom and 3 hydrogen atoms, is produced on Earth primarily by anaerobic bacteria. It is highly reactive and breaks down quickly in the presence of oxygen or ultraviolet light, so its presence in an atmosphere suggests either ongoing production or a source that replenishes it. In 2020, astronomers reported detecting phosphine in Venus's clouds at concentrations that seemed difficult to explain through abiotic chemistry. The announcement sparked widespread excitement and debate. Subsequent observations and reanalysis of the data have cast doubt on the detection, with some teams finding no phosphine at all, and others arguing that the signal could be explained by sulfur dioxide or other molecules interfering with the measurement. Even if phosphine is present, its interpretation is ambiguous. There are potential abiotic pathways for producing phosphine on Venus involving volcanic gases, photochemistry, or reactions in the clouds, though none have been definitively demonstrated. The possibility that phosphine is a biosignature, an indicator of life, remains open but unproven. If life does exist in Venus's clouds today, it would be a remnant population, descendants of organisms that once lived on the surface or in the oceans, that managed to transition to an aerial existence as the planet's surface became uninhabitable. Such a transition would require extraordinary evolutionary innovation, and the resulting organisms would be fundamentally different from their aquatic ancestors. The notion of an aerial biosphere is not entirely without precedent. On Earth, microbes are found throughout the atmosphere, carried aloft by winds, surviving in aerosols and cloud droplets. Some can remain viable at high altitudes, dormant until they are brought back to the surface by precipitation. However, Earth's atmosphere is not a habitat where organisms can complete their entire life cycle. They are transient visitors, not permanent residents. For Venus's clouds to host a true biosphere, organisms would need to reproduce, metabolize, and maintain populations without ever touching the surface. This would require nutrient cycling within the clouds, sources of energy, and mechanisms to avoid sinking into the hot lower atmosphere or being lofted into the cold, dry upper atmosphere. The challenges are formidable. The clouds are made of concentrated sulfuric acid, which is highly corrosive. Nutrients would be scarce, limited to what is carried up from the surface by volcanic eruptions or produced photochemically in the atmosphere. Energy sources are limited to sunlight and chemical gradients. Reproduction would require that offspring remain airborne, perhaps by producing spores or droplets that stay suspended. Any organism that sinks below the clouds would be destroyed by the heat and pressure. Any that rise too high would freeze or desiccate. The habitable zone in the atmosphere is a narrow band, and maintaining position within it would require either active control or fortuitous physical properties. Despite these challenges, the idea cannot be dismissed outright. Life is remarkably inventive, and evolution operates over vast timescales, providing opportunities for adaptation that we can barely imagine. If Venusian life once existed on the surface and managed to colonize the atmosphere before the oceans disappeared, it would have had hundreds of millions of years to adapt to aerial existence. Natural selection would favor traits that enhance survival in the clouds: acid resistance, buoyancy, efficient use of scarce nutrients, tolerance of ultraviolet radiation, reproductive strategies suited to an atmospheric environment. Over time, a unique biosphere might emerge, unlike anything on Earth, a last vestige of a once thriving world. The prospect of discovering life on Venus, even microbial life in the clouds, would be profound. It would demonstrate that life is not unique to Earth, that it can arise on other worlds with different conditions. It would provide a second example of biology, allowing us to understand what is universal about life and what is particular to Earth. It would also be a poignant reminder of impermanence, of how radically a planet can change, of how life, once established, is not guaranteed to endure. Venusian life, if it exists, would be a survivor, clinging to a narrow refuge in a planet that turned hostile, a living fossil from an ancient, vanished ocean world. To test the hypothesis of life in Venus's clouds would require direct sampling. Remote observations from Earth or from orbit can provide hints, detecting molecules that might be biogenic, but they cannot provide definitive proof. We need missions that can enter the atmosphere, collect cloud particles, analyze them in situ, or return them to Earth for detailed study. Such missions are technologically challenging, given the extreme conditions, but they are feasible. Balloons or airships could float at the habitable altitude, spending days or weeks collecting data, characterizing the chemistry and searching for signs of life. Sample return, though more difficult, would allow the application of sophisticated laboratory techniques, searching for complex organic molecules, isotopic signatures of biological processes, or even preserved cellular structures. Several space agencies and research groups are considering Venus missions with these goals. NASA has selected 2 missions for the late 2020s or early 2030s. Da Vinci, which will drop a probe through the atmosphere to analyze its composition and image the surface, and Veritas, which will orbit Venus and map the surface in high resolution using radar. ESA is developing Envision, another orbiter focused on surface and atmospheric science. These missions will improve our understanding of Venus's current state and its geological history, but they are not designed specifically to search for life. More ambitious missions, such as atmospheric balloons or cloud samplers, are being proposed and studied, though funding and prioritization remain uncertain. In parallel with mission planning, scientists are working to better understand the chemistry of Venus's atmosphere, to identify which molecules could be biosignatures and which could be produced abiotically. This requires laboratory experiments simulating Venusian cloud conditions, testing how sulfuric acid droplets react with various compounds under ultraviolet radiation and in the presence of trace gases. It requires atmospheric modeling to predict the distribution of gases and particles, and how they change with altitude, time of day, and season. It requires careful reanalysis of existing data, looking for subtle signals that might have been missed or misinterpreted. The search for life on Venus is part of a broader effort to understand habitability across the solar system and beyond. Every planet and moon, with even a slim chance of hosting life, is being scrutinized. Mars, with its ancient river valleys and subsurface ice, remains a prime target. Missions like Perseverance are collecting samples that will eventually be returned to Earth for analysis, searching for microbial fossils or chemical traces of past life. The icy moons of Jupiter and Saturn, Europa and Enceladus, have subsurface oceans kept liquid by tidal heating, and those oceans might provide habitats for life. Plumes of water vapor erupting from Enceladus have been sampled by the Cassini spacecraft, revealing organic molecules and salts, evidence that the ocean is chemically active. Future missions aim to sample these plumes more thoroughly, or even land on the moons and drill through the ice to reach the oceans below. Titan, Saturn's largest moon, is another intriguing target. It has a thick nitrogen atmosphere, lakes and seas of liquid methane and ethane on its surface, and a subsurface water ocean. The surface environment is cold, around minus 180 degrees Celsius. Far too cold for water-based life, but the presence of liquid hydrocarbons and complex organic chemistry raises the possibility of exotic forms of life based on different solvents and biochemistries. The Dragonfly mission, scheduled to launch in the late 2020s, will send a rotorcraft to explore Titan's surface, analyzing the organic chemistry and searching for prebiotic or even biotic processes. Beyond the solar system, exoplanet science has revealed thousands of planets orbiting other stars, many of them in the habitable zones where liquid water could exist on their surfaces. Characterizing the atmospheres of these planets, searching for gases like oxygen, methane, or phosphine that might indicate life, is a major goal of current and future telescopes. The James Webb Space Telescope, launched in 2021, is beginning to observe exoplanet atmospheres in unprecedented detail, though detecting definitive biosignatures remains challenging. Future telescopes, larger and more sensitive, will continue this work, building a statistical picture of how common habitable planets are and whether life is rare or abundant in the galaxy. Venus fits into this larger picture as a cautionary tale and a test case. If Venus was once habitable and lost that habitability, it demonstrates that planets can transition from life-supporting to life-extinguishing. This is relevant for understanding exoplanets. Many of the rocky planets discovered around other stars are closer to their suns than Earth is to ours, receiving more intense radiation, and thus more likely to be in a Venus-like state than an Earth-like state. Understanding the conditions under which a planet becomes a Venus rather than an Earth helps us assess the habitability of exoplanets and refine our search strategies. Moreover, Venus provides an opportunity to study the end state of a runaway greenhouse, to see in detail what happens when climate feedback loops spiral out of control. This has implications for Earth. While Earth is not in immediate danger of becoming Venus, the ongoing increase in carbon dioxide due to human activities is raising global temperatures, melting ice, shifting weather patterns, and acidifying oceans. Understanding the mechanisms that drive extreme climate change on Venus can inform our understanding of Earth's climate system, highlighting which feedbacks are most dangerous and what thresholds we should avoid crossing. The study of planetary climate is inherently comparative. No planet is an island. Each world we study provides data points, examples of how physics, chemistry, and geology interact to create climates. Earth is our only example of a continuously habitable planet, but Mars, Venus, Titan, and the exoplanets provide contrasts, showing what happens under different conditions. By studying Venus's history and current state, we learn not just about Venus but about the general principles governing planetary habitability. Returning to the question of early Venus, the evidence is circumstantial but suggestive. The deuterium enrichment indicates substantial water loss, implying that Venus once had more water than it does now. Climate models show that, under certain assumptions, early Venus could have maintained liquid water on its surface for hundreds of millions to a few billion years, depending on initial water content, cloud properties, and the evolution of solar luminosity. The geological record, such as it is, shows a planet dominated by volcanism, but with few features that can be definitively dated to the first billion years. The surface we see today is relatively young, shaped by processes that occurred long after any habitable period would have ended. There are tantalizing hints in the atmospheric composition. Venus's atmosphere contains trace amounts of water vapor, a few tens of parts per million, enough to measure but far less than the saturated steam atmosphere that would have existed during the runaway greenhouse. There are also trace gases like sulfur dioxide, carbon monoxide, and hydrogen sulfide, products of volcanic outgassing and atmospheric chemistry. The ratios of isotopes in these gases, particularly the ratios of noble gas isotopes like argon and neon, provide clues about the planet's formation and the loss of its atmosphere over time. Argon-36, a light isotope, is depleted relative to argon-38, a heavier isotope, suggesting preferential loss of the lighter isotope consistent with atmospheric erosion by the solar wind. Neon isotopes show similar patterns. These measurements, while technical, help constrain models of atmospheric evolution and the timing of water loss. Another piece of the puzzle comes from the study of Venus's surface mineralogy. Although we have not sampled many locations directly, radar observations from orbit can distinguish between different rock types based on their reflectivity and surface roughness. Some highland regions on Venus have high radar reflectivity, suggesting the presence of minerals that form under cooler, wetter conditions than currently exist. One hypothesis is that these are weathering products, such as iron pyrite or other sulfide minerals that form when volcanic rocks interact with sulfur-rich gases in the atmosphere. However, another hypothesis is that these minerals are remnants from an earlier, wetter era, when liquid water was present. Distinguishing between these interpretations requires better data, ideally from landers that can analyze the rocks directly. There, organisms or chemical precipitation combine these ions with dissolved carbon dioxide to form carbonate minerals, which settle to the seafloor and are eventually subducted into the mantle at tectonic plate boundaries. Volcanism then releases carbon dioxide back into the atmosphere, completing the cycle. When the planet warms, weathering accelerates, drawing down more carbon dioxide and cooling the planet. When the planet cools, weathering slows, allowing volcanic carbon dioxide to accumulate and warm the planet again. This negative feedback, operating over millions of years, has helped maintain liquid water on Earth's surface despite the gradual brightening of the Sun. Venus likely experienced similar processes early in its history, but with a critical difference: its proximity to the Sun. Even with the Sun emitting only 70% of its current luminosity, Venus received significantly more solar energy per square meter than Earth. This higher energy input meant that Venus's surface was warmer, and a warmer surface leads to higher rates of evaporation if liquid water is present. Water vapor is itself a potent greenhouse gas, more effective per molecule than carbon dioxide at trapping infrared radiation. A warmer Venus would have had more water vapor in its atmosphere, which would have trapped more heat, leading to further warming, more evaporation, more water vapor, and so on. This is a positive feedback, a runaway process that can spiral out of control. At a certain threshold, the amount of water vapor in the atmosphere becomes so great that the planet enters a runaway greenhouse state. In this condition, the infrared radiation emitted by the surface is entirely absorbed by water vapor and carbon dioxide in the atmosphere, preventing any heat from escaping to space. The surface temperature rises until it reaches equilibrium, dictated not by radiation to space from the surface, but by radiation to space from the upper atmosphere. For a planet like Venus, this equilibrium temperature can exceed several hundred degrees Celsius. At such temperatures, the oceans boil. The entire water inventory of the planet is injected into the atmosphere, creating a thick steam atmosphere that persists until photodissociation and hydrogen escape gradually remove the water over tens to hundreds of millions of years. Climate models suggest that Venus may have entered a runaway greenhouse very early in its history, possibly within the first few 100 million years after formation. However, these models are sensitive to initial conditions, particularly the amount of water present and the details of cloud formation. Clouds can reflect sunlight back into space, providing a cooling effect that partially counteracts greenhouse warming. If Venus formed with less water than Earth, or if its early cloud cover was particularly reflective, it might have maintained liquid water on its surface for a longer period, perhaps a billion years or more. Some models indicate that if Venus had oceans, and if those oceans covered a significant fraction of the surface, the planet might have remained habitable for over 2 billion years, provided that plate tectonics or some analogous process recycled carbon dioxide and prevented it from accumulating to runaway levels. The possibility of a temperate, ocean-covered early Venus is tantalizing. If such conditions persisted for even a few 100 million years, this would have provided a window for the origin of life. On Earth, life appears to have emerged relatively quickly in geological terms. The oldest undisputed fossils of microorganisms date to about 3.5 billion years ago, preserved in rocks from Australia and South Africa. However, evidence for life may extend further back. Carbon isotope ratios in ancient sediments suggest biological activity as early as 3.8 billion years ago, and some researchers argue for even earlier origins based on chemical signatures and structures in rocks from Greenland. If life arose on Earth within the first few 100 million years after the planet became habitable, the same could plausibly have occurred on Venus, provided Venus offered similar conditions during a similar time frame. What would early Venus have looked like if it possessed liquid water? Imagine a world with shallow seas, perhaps not as deep or as extensive as Earth's oceans, but present nonetheless. The surface temperature would have been higher than early Earth, possibly tropical or even supertropical, with average temperatures ranging from 30 to 60 degrees Celsius or more, depending on atmospheric composition and cloud cover. The atmosphere would have been dense, rich in carbon dioxide and water vapor, with a greenhouse effect strong enough to keep water liquid despite the faint young sun, but not yet strong enough to trigger runaway evaporation. The Soviet Venera and Vega missions, which landed on Venus in the 1970s and 80s, provided the only in situ analyses of Venusian soil to date. They found basaltic compositions, similar to volcanic rocks on Earth and Mars, with varying amounts of potassium, uranium, and thorium. Some landing sites showed rocks with compositions similar to Earth's granitic rocks, which typically form in the presence of water. However, the measurements were limited, and the interpretation is not straightforward. Granite-like compositions can also result from partial melting of basalt in the absence of water, so the presence of such rocks does not definitively prove that water was present. Future missions could target these high reflectivity regions, landing in the highlands to directly measure the mineralogy and look for signatures of past water. Such missions would face significant engineering challenges, as the surface conditions remain extremely hostile, but the scientific payoff would be substantial. Confirming the presence of minerals that require water for their formation would strengthen the case that Venus once had liquid water and, by extension, that it was once habitable. The story of Venus is also a story about the limits of habitability. Habitability is not a binary state, but a spectrum, a set of conditions that more or less favor the presence of life. Liquid water is often cited as a requirement, but the temperature range, pressure range, and chemical composition of that water all matter. Life on Earth tolerates a range of salinities, pH values, and solute concentrations, but there are limits. Water that is too acidic, too alkaline, too salty, or too hot may not support life, even if it is technically liquid. On Venus, if oceans existed, their chemistry would have been influenced by the composition of the rocks, the gases in the atmosphere, and the interactions between the two. The oceans would have been acidic, due to dissolved carbon dioxide forming carbonic acid, and perhaps sulfuric acid from volcanic sulfur dioxide. The temperature would have been high, possibly 50 to 70 degrees Celsius or more. These conditions are extreme but not necessarily sterile. Hot, acidic springs on Earth host microbial life, and the deep biosphere in Earth's crust contains organisms living in high-temperature, high-pressure environments with limited nutrients and energy. If Venusian life existed, it would have been adapted to these harsh conditions from the start. The concept of a habitable zone around a star is commonly used in astrobiology to identify where planets might have liquid water. This zone is defined by the range of distances from the star at which a planet with a suitable atmosphere can maintain surface temperatures between the freezing and boiling points of water. Earth lies comfortably within the Sun's habitable zone. Mars is near the outer edge, too cold for liquid water on the surface under current conditions, though it may have been warmer in the past. Venus is near the inner edge, receiving more solar energy than Earth, but potentially still within the habitable zone when the Sun was younger and dimmer. However, the habitable zone is a simplification. It assumes a planet with an Earth-like atmosphere and does not account for differences in planetary mass, rotation rate, atmospheric composition, cloud cover, or geological activity. Two planets at the same distance from the same star can have radically different climates depending on these factors. Venus and Earth are a prime example. Despite being near the inner edge of the habitable zone, Venus is not habitable due to its runaway greenhouse atmosphere. Conversely, planets farther from their stars than the nominal habitable zone might still be habitable if they have thick atmospheres with potent greenhouse gases, or if they have subsurface oceans heated by tidal forces or radioactive decay. The realization that habitability depends on a complex interplay of factors has led to the concept of the habitable zone being refined and expanded. Some researchers now speak of the conservative habitable zone, the region where liquid water can exist under the most pessimistic assumptions, and the optimistic habitable zone, the region where liquid water might exist under more favorable assumptions. Others define different types of habitable zones. The surface habitable zone, where liquid water can exist on a planet's surface. The subsurface habitable zone, where liquid water can exist beneath the surface. And the cloud habitable zone, where conditions in the atmosphere might support life. Venus, having lost its surface habitability, might still fall within the cloud habitable zone, at least at certain altitudes. The diversity of potentially habitable environments expands the possibilities for where life might exist. Life does not require an Earth clone. It requires energy, nutrients, a suitable solvent, and stable conditions for at least some period of time. These requirements can be met in many different environments, from surface oceans to subsurface aquifers, to atmospheric cloud layers to hydrothermal vents on icy moons. Each environment presents unique challenges and opportunities, and life, if it arises, will be shaped by those conditions. On Venus, the unique challenge is the intensity of the greenhouse effect and the rate at which conditions changed. If the transition from habitable to uninhabitable was rapid, occurring over a few million years, any life present would have had little time to adapt. Species would go extinct, ecosystems would collapse, and only the most resilient organisms might survive long enough to find new niches. If the transition was slower, occurring over tens or hundreds of millions of years, evolution might have kept pace, with organisms gradually shifting their ranges, adapting to higher temperatures, higher acidity, lower water availability, until they ran out of viable habitats. The pace of climate change is a critical factor in determining the outcome. On Earth, past climate changes have varied in speed. Some, like glacial interglacial cycles driven by orbital variations, occur over tens of thousands of years, allowing ecosystems to migrate and adapt. Others, like the asteroid impact that ended the Cretaceous period and killed the dinosaurs, occur over days to years, giving no time for adaptation and causing mass extinction. The current human-driven climate change is occurring over decades to centuries, faster than most natural climate changes but slower than catastrophic events. The Venusian runaway greenhouse, once initiated, may have progressed over millions of years, a timescale intermediate between slow and fast, enough time for some organisms to adapt but not enough to prevent eventual extinction. If life on Venus did go extinct, it would have left no fossils in the conventional sense. The high surface temperatures would destroy organic molecules, and the volcanic resurfacing would have buried or melted any ancient rocks that might have contained fossils. The only potential repositories of ancient biological material would be in locations that escaped resurfacing, such as the highlands, or in the atmosphere, if microbes managed to persist there. Detecting such fossils would require missions that can analyze rocks or atmospheric samples with great sensitivity, searching for complex organic molecules, isotopic anomalies, or microscopic structures that resemble cells. The concept of a biosignature is central to the search for life beyond Earth. A biosignature is any substance, structure, or pattern whose presence indicates the existence of life, either past or present. On Earth, fossils are biosignatures, as are stromatolites, as are isotopic ratios in ancient rocks that suggest biological fractionation of carbon. In the context of Venus, potential biosignatures might include specific organic molecules in the clouds, such as amino acids or lipids, that are difficult to produce abiotically in Venusian conditions. They might include gases like phosphine, if its presence can be confirmed and abiotic production ruled out. They might include cellular structures or organized patterns in cloud particles, visible under a microscope, that suggest biological organization. However, biosignatures can be ambiguous. Non-biological processes can produce molecules and structures that resemble biological ones. Amino acids can form in interstellar space and be delivered by meteorites. Lipids can form through Fischer-Tropsch-type reactions in hydrothermal systems. Patterns that look like cells can arise from chemical precipitation or mineral formation. This is why the search for life requires multiple lines of evidence, corroborating observations that together build a compelling case. A single molecule or structure is rarely definitive. A suite of molecules in ratios characteristic of biology, combined with isotopic signatures consistent with metabolic fractionation, combined with structures that resemble cells and show signs of organization, would be much more convincing. The history of the search for life on Mars illustrates these challenges. In 1996, a team of scientists announced that a meteorite from Mars, designated ALH 84001, contained evidence of ancient Martian life. The meteorite, found in Antarctica, contained carbonate minerals, polycyclic aromatic hydrocarbons, magnetite crystals, and structures that resembled bacteria. Each piece of evidence, taken alone, could be explained by non-biological processes, but the team argued that the combination was best explained by biology. The announcement generated enormous excitement but also intense skepticism. Subsequent research showed that the magnetite crystals and organic molecules could form abiotically, and the bacteria-like structures might be artifacts or mineral formations. The consensus today is that the evidence is inconclusive. The meteorite might contain signatures of life, but it might not. The debate continues, underscoring the difficulty of proving the existence of life from indirect evidence. For Venus, the burden of proof will be similarly high. Claims of life, especially extraordinary claims like life existing in the clouds of a planet as hostile as Venus, require extraordinary evidence. The scientific community will demand multiple independent observations, rigorous testing of alternative explanations, and reproducible results. This is as it should be. Science progresses by skepticism and verification, by proposing hypotheses and then trying to disprove them, by building consensus through accumulation of evidence. Yet the pursuit is worth the effort. The question of whether Venus once had life goes to the heart of our understanding of life's place in the universe. If life arose independently on two planets in the same solar system, it suggests that the origin of life is a relatively probable event, given suitable conditions. This would imply that life is common throughout the galaxy, arising wherever planets offer the right combination of chemistry and energy. Conversely, if Venus was habitable for a significant period and life did not arise there, despite arising on Earth, it suggests that the origin of life is rare, requiring not just suitable conditions but also fortuitous circumstances, perhaps rare events or unlikely chemical pathways. The study of Venus's past also informs our understanding of planetary evolution. Planets are not static. They change over time, driven by internal heat, external energy input, and the complex interactions between atmosphere, surface, and interior. Some changes are gradual, like the brightening of the sun or the slow cooling of a planet's core. Others are abrupt, like asteroid impacts or volcanic eruptions. Understanding how these processes play out over billions of years, how they influence habitability, and how they can lead to dramatic transitions like the runaway greenhouse on Venus is essential for predicting the fate of planets around other stars. There is a philosophical dimension to this inquiry as well. Venus serves as a reminder of impermanence, of how much can be lost. If Venus once had oceans, rivers, perhaps life, all of that is gone now, erased by processes that transformed the planet into a hellscape. This raises questions about the value and fragility of habitability, about how we should regard our own planet. Earth is currently habitable, but this state is not guaranteed to last forever. On timescales of billions of years, the sun will continue to brighten, eventually making Earth too hot for liquid water, initiating our own runaway greenhouse. This is not an immediate concern, as it will take perhaps 1 billion years or more, but it is an eventual inevitability. On shorter timescales, human activities are changing Earth's climate, increasing carbon dioxide concentrations, raising temperatures, and altering ecosystems. While we are not in danger of turning Earth into Venus, we are demonstrating that climate can be destabilized, that feedbacks can be triggered, and that the consequences can be severe. Venus is a stark example of what happens when greenhouse gases accumulate without limit, when feedbacks amplify warming, when a planet crosses tipping points. The specifics are different, the mechanisms are different, but the underlying physics is the same. Understanding Venus helps us understand the risks we face. The loss of habitability on Venus also prompts reflection on the fleeting nature of windows of opportunity. If Venus was habitable for a few 100 million years, or even 1 billion years, this is a brief moment in the planet's 4.5 billion year history. It is a window that opened and then closed. If life arose during that window, it flourished temporarily and then perished. This pattern may be common on rocky planets. Many exoplanets may have had habitable periods that ended as their stars brightened or their atmospheres changed. Life may have arisen, evolved, and gone extinct on countless worlds, leaving no trace that we can detect from light years away. This possibility, that life is not only rare but also transient, adds a layer of urgency to the search for life. If most habitable environments are temporary, then we are unlikely to find intelligent civilizations that have persisted for millions of years. Instead, we might find simple life, or the remnants of extinct life, or planets in transition between habitable and uninhabitable states. Venus might be our closest example of the latter, a planet caught in the aftermath of a habitability crisis, offering a glimpse of what many exoplanets might look like. Contemplating Venus also evokes a sense of tragedy. If life existed there, it is gone. The oceans are gone. The blue skies are gone, replaced by a choking, corrosive atmosphere and a surface hot enough to glow. There is no rescue, no reversal. The processes that created the current Venus are irreversible on human timescales, and perhaps on geological timescales as well. Even if we could somehow engineer the planet's atmosphere, removing the carbon dioxide and cooling the surface, the water is gone, escaped to space, and would need to be imported from elsewhere, a task of staggering difficulty. Venus is lost, and if it once harbored life, that life is lost with it. Yet there is also a kind of resilience in the possibility of life in the clouds. If Venusian microbes do exist, drifting in the habitable layer of the atmosphere, they represent an extraordinary act of survival, a refusal to go extinct despite overwhelming odds. They would be a testament to the tenacity of life, to its ability to adapt and persist in the face of catastrophe. Studying such life, if we can find it, would reveal strategies for survival in extreme environments, biochemical innovations that allow existence in conditions we can barely imagine. It would expand our understanding of what life can be and where it can go. The exploration of Venus, whether to search for life or to understand its history, is fundamentally an act of curiosity. We are driven to know, to understand, to piece together the story of how a world so similar to our own became so different. This curiosity is a defining feature of our species. We build telescopes, spacecraft, instruments, and missions to satisfy this drive, to answer questions that have no immediate practical application but which speak to our desire to comprehend the universe and our place in it. In recent years, interest in Venus has been reinvigorated, after decades during which Mars received the majority of attention and resources. The detection of phosphine, controversial as it is, served as a catalyst, reminding the scientific community and the public that Venus is a world worth studying. Missions are being planned, technologies are being developed, and new data will soon begin to flow. The 2030s may be a decade of Venus exploration, with multiple spacecraft arriving at the planet, providing a coordinated, multi-platform study of its atmosphere, surface, and interior. These missions will address fundamental questions. How does the atmosphere circulate? Venus's upper atmosphere rotates much faster than the surface, a phenomenon known as superrotation, with winds reaching speeds of over 300 kilometers per hour at the cloud tops, while the surface rotates slowly. The mechanisms driving this superrotation are not fully understood, involving complex interactions between solar heating, atmospheric waves, and the transfer of momentum. Understanding superrotation on Venus helps us understand atmospheric dynamics on other planets, including rapidly rotating gas giants and tidally locked exoplanets. What is the composition of the lower atmosphere, near the surface, where conditions are most extreme? The Soviet landers provided some data, but only from a few locations and only for a limited time. New missions with improved instruments could measure trace gases, noble gas isotopes, and isotopic ratios of carbon and oxygen, providing clues about volcanic activity, atmospheric chemistry, and the history of water loss. What is happening in the planet's interior? Venus is similar in size to Earth and should have similar internal heat production from radioactive decay. Yet the lack of plate tectonics and the uncertain timing of volcanic resurfacing suggests that heat loss on Venus operates differently. Is the mantle convecting in a single-cell pattern or in multiple cells? Is the lithosphere rigid, or does it deform slowly? Are there active volcanoes today, releasing fresh lava and gases into the atmosphere? Some observations suggest that the abundance of sulfur dioxide in the atmosphere has varied over time, which could indicate episodic volcanic eruptions, but this is not confirmed. How has the surface evolved? Detailed radar mapping can identify volcanic features, tectonic structures, and impact craters, allowing reconstruction of the planet's geological history. Distinguishing between different ages of lava flows, identifying ancient terrain that might have escaped resurfacing, and mapping mineralogical variations can all contribute to understanding whether Venus had a habitable past and when it ended. Each of these questions connects to the overarching question of habitability. Understanding atmospheric dynamics helps us understand how heat is distributed and whether there are microclimates or refugia. Understanding surface composition helps us identify signatures of past water. Understanding volcanic activity helps us understand the delivery of gases to the atmosphere and the potential for subsurface environments, such as hydrothermal systems that might have hosted life in the past or even today. There is also the question of Venus's magnetic field, or lack thereof. If Venus once had a magnetic field and lost it, when did this happen? Did the loss of the field contribute to the loss of the atmosphere and water? Measuring the residual magnetism in ancient rocks, if such rocks can be found, would provide a record of past magnetic field strength and direction, but this requires landing in locations that have not been resurfaced. The study of Venus also intersects with the study of tectonic processes. On Earth, plate tectonics is driven by the descent of cold, dense oceanic lithosphere into the mantle at subduction zones. The sinking slab pulls the rest of the plate along, creating motion. This process requires water to weaken the rocks and allow the lithosphere to bend and sink. Venus, lacking water, cannot have Earth-like plate tectonics, but it might have other forms of tectonics. Observations suggest that parts of the crust have been compressed, forming mountain belts, and other parts have been extended, forming rift zones. These features indicate that the lithosphere is deforming, even if it is not broken into discrete plates. Understanding these deformation patterns helps us understand how heat escapes from the planet and how the surface has been shaped. The comparison between Earth and Venus also highlights the role of the Moon. Earth has a large moon, formed by a giant impact early in its history. The Moon stabilizes Earth's axial tilt, preventing large variations that could lead to extreme climate swings. The Moon also creates tides, which mix the oceans and may have played a role in the origin of life by concentrating organic molecules in tidal pools. Venus has no moon. Its rotational axis is tilted by only a few degrees, and it has no significant tides. Whether the absence of a moon influenced Venus's evolution is unclear, but it is a difference worth considering. Another difference is the impact history. Both Earth and Venus experienced heavy bombardment early in their histories, a period when asteroids and comets frequently collided with the planets. On Earth, some of the largest impacts may have vaporized the oceans, sterilizing the planet and resetting any prebiotic chemistry or early life. However, life on Earth appears to have emerged during or shortly after this period, suggesting that the impacts did not prevent life from taking hold, and may even have delivered water and organic molecules that facilitated it. Venus would have experienced a similar bombardment. If the impacts were large enough, they could have temporarily replenished Venus's water inventory, potentially extending the habitable period. Alternatively, large impacts could have stripped away atmosphere, hastening the loss of water. The interplay between impacts, volcanism, and climate on early Venus is complex. Volcanic eruptions release gases, including water vapor, carbon dioxide, and sulfur dioxide. If volcanism was more vigorous on early Venus than it is today, the outgassing rate would have been higher, potentially maintaining a thick atmosphere even as hydrogen escaped to space. However, a thick atmosphere also means a stronger greenhouse effect, which could trigger the runaway greenhouse sooner. The balance between outgassing, escape, and greenhouse warming determines the duration of the habitable window. Modeling these processes requires sophisticated computer simulations that couple atmospheric dynamics, surface processes, and interior heat flow. Such models have been developed for Earth and are being adapted for Venus, but they are limited by uncertainties in initial conditions and parameters. We do not know how much water Venus started with, how reflective the early clouds were, how much carbon dioxide was in the early atmosphere, or how quickly the sun brightened. Each of these factors affects the outcome, and small changes in assumptions can lead to large changes in the modeled climate. To reduce these uncertainties, we need more data. Data from Venus itself, from its atmosphere, surface, and interior, but also data from other planets and exoplanets, providing comparison points and tests of the models. Each new discovery refines our understanding, narrows the range of possibilities, and brings us closer to answering the question of whether Venus once had life. There is also the possibility of studying ancient Earth as an analog for early Venus. The Archean Eon, from 4 to 2.5 billion years ago, was a time when Earth's atmosphere was different, when the sun was dimmer, and when life was just beginning. Rocks from this period, though rare and altered by metamorphism, preserve clues about the conditions under which early life evolved. Studying these rocks, the isotopic compositions of the minerals, the structures of the stromatolites, the chemistry of the sediments, helps us understand what early habitable environments looked like. This understanding can then be applied to Venus, asking whether similar conditions might have existed there. The concept of habitability also extends beyond the presence of liquid water. Liquid water is necessary for life as we know it, but there might be other solvents that could support life. Ammonia, methane, and sulfuric acid have all been proposed as alternative solvents, each with different properties that would require different biochemistries. Ammonia is liquid at lower temperatures than water and is a good solvent for many compounds. Methane is liquid at very low temperatures, as seen on Titan. Sulfuric acid, despite being corrosive to Earth life, might be usable by organisms adapted to acidic environments. If Venus's clouds contain sulfuric acid droplets, and if organisms could use sulfuric acid as a medium, this would expand the potential for habitability in the clouds. However, these alternative biochemistries are speculative. We have no examples of life using solvents other than water. All life on Earth, despite its diversity, shares a common biochemistry based on water, carbon, and a specific set of elements and molecules. This suggests that water-based life is not just one option among many, but is perhaps the most chemically favorable. Water has unique properties. It is an excellent solvent, it remains liquid over a wide temperature range at moderate pressures, it has high heat capacity and thermal conductivity, and it participates in many biochemical reactions. Other solvents may lack some of these properties, making them less suitable for life. Until we find life based on alternative biochemistries, water remains the focus of the search for habitability. Returning to the narrative of Venus's transformation, we can imagine the final days of the Venusian oceans. As the runaway greenhouse takes hold, the surface temperature climbs, passing the boiling point of water at Venusian atmospheric pressure. The pressure is high, perhaps several times Earth's atmospheric pressure, so water can remain liquid at temperatures above 100 degrees Celsius, possibly up to 150 degrees or more. But eventually, even at high pressure, the water boils. The oceans begin to evaporate, not gradually but catastrophically. Steam fills the atmosphere, forming dense clouds that trap even more heat. The surface temperature rises further, accelerating evaporation. The entire ocean, whatever its depth, is converted to vapor within a geologically short time, perhaps 1,000,000 years, perhaps less. The steam atmosphere is thick, opaque, and incredibly hot. The surface pressure increases as water vapor accumulates, potentially reaching dozens or even hundreds of atmospheres. The planet is shrouded in a dense fog, illuminated only by the dim red glow of the molten surface below. The greenhouse effect is at its peak, with infrared radiation completely trapped, unable to escape to space. The temperature at the surface might reach 700 degrees Celsius or higher, enough to melt some minerals. In the upper atmosphere, water vapor is exposed to ultraviolet radiation from the sun. Photons break the molecular bonds, splitting water into hydrogen and oxygen. The hydrogen atoms, being light, move fast enough to escape the planet's gravity, especially at the high temperatures of the upper atmosphere. They stream away into space, carried off by thermal motion and interactions with the solar wind. The oxygen atoms, being heavier, do not escape as readily. They accumulate, reacting with each other to form molecular oxygen, or reacting with volcanic gases like sulfur dioxide or carbon monoxide. Over tens of millions of years, the hydrogen continues to escape, and the oxygen continues to be sequestered. The steam atmosphere gradually thins, but it is not replaced by water. The oceans are gone, lost to space, and locked in rocks. Carbon dioxide, continuously outgassed by volcanoes, begins to dominate the atmosphere. With no oceans to dissolve the carbon dioxide and no liquid water to drive weathering, the carbon dioxide accumulates. The atmosphere transitions from steam to carbon dioxide, maintaining the greenhouse effect even as the water disappears. The surface cools slightly, no longer sustained by the latent heat of vaporization, but it remains hot, hundreds of degrees above the boiling point of water, locked in by the thick carbon dioxide blanket. This is the Venus that stabilizes, the Venus that persists for billions of years. The atmosphere is 90 times thicker than Earth's, composed almost entirely of carbon dioxide, with clouds of sulfuric acid and trace amounts of water vapor, sulfur dioxide, and other gases. The surface is dry, barren, shaped by volcanism and thermal stress. The temperature is uniform, day and night, equator to pole, maintained by the slow rotation and the efficient greenhouse effect. There is no weather in the sense of changing conditions, only the slow, eternal circulation of the dense atmosphere and the occasional volcanic eruption. If life existed on Venus before this transition, it was extinct by the end. No organism can survive complete desiccation in temperatures exceeding 400 degrees. The biochemical molecules break down, the cellular structures disintegrate, the information encoded in DNA or its analog is destroyed. Even extremophiles, the hardiest organisms on Earth, have limits. Tardigrades can survive desiccation and extreme temperatures for short periods by entering a cryptobiotic state, but they cannot remain in that state indefinitely, and they require water to revive. Venusian life, if it existed, would have faced conditions beyond the tolerance of any known organism, and there would have been no refugia, no pockets of habitability where survival was possible. Unless, as speculated earlier, life managed to colonize the atmosphere before the surface became uninhabitable. This would require that the transition from surface to atmosphere occurred gradually enough for evolution to act, and that the atmosphere offered suitable conditions even as the surface deteriorated. It is a narrow path, requiring a sequence of unlikely events, but not impossible. If it occurred, the descendants of that life might still exist today, hidden in the clouds, awaiting discovery. The search for such life is, in many ways, a search for a lost world. We cannot visit the ancient Venus, cannot see its oceans or walk its shores. We can only infer its existence from models, measurements, and the faint traces left behind. But if we find life in the clouds, it would be a direct connection to that lost world, a surviving fragment that carries information about what Venus was like billions of years ago. The biochemistry, the genetics, the metabolic pathways of cloud-dwelling Venusian microbes would reflect their origin in a different environment, an environment that no longer exists. Studying them would be like studying a living fossil, an organism that has changed little since its ancestors lived in the ancient seas. There is an analogy here with extremophiles on Earth. Many of the most extreme organisms, living in hot springs, deep sea vents, and subsurface rocks, are members of the domain Archaea, one of the 3 domains of life. Archaea are thought to be ancient, possibly representing lineages that diverged early in the history of life. Their biochemistry is distinct from that of bacteria and eukaryotes, reflecting their adaptation to extreme conditions. Some researchers believe that life on Earth originated in hot, high-pressure environments, and that the extremophiles we see today are descendants of the earliest organisms. If so, studying extremophiles gives us insight into early life on Earth. Similarly, if Venusian cloud microbes exist, they might represent an ancient lineage adapted to conditions that prevailed on early Venus. Their biochemistry might reveal features of a lost biosphere, providing clues about how life originated and evolved on a world that is now radically different. Even if they are not directly related to organisms that lived on the surface, their adaptations to cloud life might reflect evolutionary solutions to challenges that no longer exist elsewhere on the planet. The philosophical implications extend further. If life arose independently on Venus and Earth, it suggests that life is a natural outcome of chemistry, something that emerges whenever conditions are right. This would support the view that the universe is likely teeming with life, that we are not alone, that biology is as fundamental as physics or chemistry. On the other hand, if Venus was habitable and life did not arise there, or arose and left no trace, it suggests that the origin of life is difficult, requiring not just suitable conditions but also rare events or specific circumstances. This would support the view that life is rare, that Earth is unusual, that we may be isolated in a vast, mostly lifeless cosmos. Both views have profound consequences for how we see ourselves and our future. If life is common, then the universe is a rich tapestry of biological diversity, and the search for life and intelligence beyond Earth is likely to succeed eventually. If life is rare, then Earth is precious, a unique oasis in a barren desert, and the survival of life may depend on what happens here. The study of Venus contributes to resolving this question, providing one more data point in the sparse sample of planets we can study in detail. The concept of a lost biosphere also resonates with concerns about Earth's future. We live in a time of rapid environmental change, driven by human activities. Species are going extinct at rates not seen since the last mass extinction 66 million years ago. Ecosystems are being disrupted, climate is changing, and the chemistry of the oceans and atmosphere is being altered. While Earth is not in danger of becoming Venus anytime soon, the example of Venus reminds us that planets can change, that habitability is not permanent, and that once lost, it may not be recoverable. There is a moral dimension to this as well. If Venus once had life and we are capable of discovering evidence of that life, we have a responsibility to do so carefully, ethically, and with respect for what that life represents. If we send missions to Venus and find microbes in the clouds, we must ensure that our exploration does not contaminate or harm them. This is the principle of planetary protection, the idea that we should not disrupt potential ecosystems on other worlds, and that we should avoid bringing Earth organisms to other planets where they might interfere with native life or compromise scientific investigations. Planetary protection is a practical challenge for Venus missions. Spacecraft entering the atmosphere or landing on the surface must be sterilized to prevent Earth microbes from hitching a ride. However, sterilization is difficult. Microbes are incredibly resilient, and some can survive extreme heat, radiation, and desiccation. Standard sterilization procedures involve heating spacecraft to high temperatures or exposing them to radiation, but these processes can damage sensitive instruments. For missions to Venus's clouds, the challenge is even greater, as the environment at 50 kilometers altitude is relatively benign, and Earth microbes might survive there, potentially contaminating the very environment we are trying to study. Balancing the desire for exploration with the need for planetary protection requires careful planning, rigorous protocols, and international cooperation. Space agencies have established guidelines, and missions to potentially habitable environments undergo stringent reviews. Yet the guidelines evolve as our understanding improves, and as missions become more ambitious, reaching deeper into planetary environments, the risks of contamination increase. There is also the reverse concern. If we bring samples back from Venus, we must ensure that they do not contaminate Earth. This is forward contamination versus backward contamination. If Venusian microbes exist and we bring them to Earth, they would need to be contained in secure facilities, studied under quarantine, to prevent any possibility of them escaping and affecting Earth's biosphere. The risk is probably low, as Venusian life, if it exists, would be adapted to very different conditions and unlikely to survive or reproduce in Earth's environment. But the possibility cannot be dismissed, and the protocols for sample return missions include strict containment measures. These considerations illustrate the complexity of astrobiology, which is not just a search for life, but an interdisciplinary endeavor involving biology, chemistry, geology, planetary science, engineering, ethics, and philosophy. Each mission, each discovery, each new piece of data contributes to a larger picture, a growing understanding of how life relates to the universe, how it arises, persists, and perhaps ends. Venus stands at the center of this inquiry, a world that might have been a sibling to Earth, might have hosted life, and might still, in some tenuous form, harbor remnants of that life. The exploration of Venus is an exploration of possibilities, an attempt to reconstruct a history that is lost, to imagine a world that no longer exists, to find traces of life in a place where life seems impossible. As we look forward to future missions, to the data they will return, to the questions they will answer and the new questions they will raise, we are reminded that the pursuit of knowledge is a journey without end. Each answer leads to deeper questions. Each discovery opens new mysteries. Venus, once dismissed as a hellish, lifeless wasteland, is now recognized as a world with a story, a history, and perhaps a biology. The story is still being written, the history still being reconstructed, and the biology, if it exists, still waiting to be discovered. The transformation of Venus from a potentially habitable world to the inferno we see today is a narrative of loss, but it is also a narrative of persistence, of the possibility that life, once seeded, might find ways to endure even as the world changes around it. It is a narrative that challenges our assumptions, that expands our imagination, and that reminds us of the diversity of planetary fates. Not all Earths remain Earths. Some become Venuses. Understanding why and what that means for life is one of the great scientific challenges of our time. The question of whether Venus once had life and lost it all may never be answered with certainty. The evidence is fragmentary, the signals ambiguous, and the passage of billions of years has erased much of the record. But the pursuit of the answer is itself valuable, driving innovation, inspiring missions, and deepening our understanding of planets, climate, and life. Whether we find definitive proof of past life, or only constraints on what might have been, or tantalizing hints that keep the question open, the effort will have been worthwhile. Venus, in its silence, in its brilliance in the evening sky, in the data transmitted by spacecraft that brave its atmosphere, speaks to us across the void. It tells a story of a world transformed, of oceans that boiled away, of skies that became furnaces, of life, perhaps, that arose and vanished. It is a story written in the language of physics and chemistry, decoded by the tools of science, interpreted through the lens of our growing understanding. It is a story that is, in the end, a mirror held up to Earth, reflecting not what we are, but what we might become if the delicate balance that sustains us is broken. And so we continue to watch Venus, to study it, to send our emissaries into its hostile embrace, seeking answers to questions that reach back billions of years and extend forward to the fate of worlds beyond our solar system. In the search for life on Venus, we search for a connection, a thread that links us to other biospheres, other origins, other evolutionary pathways. We search for reassurance that life is robust, or for warning that it is fragile. We search for understanding, for knowledge, for the satisfaction of curiosity that defines us as a species. Venus, whether it once had life or not, whether it harbors life now or not, remains a compelling target, a puzzle worth solving, a world worth knowing. The amber glow persists, unchanging, as Venus rotates slowly beneath its veil of clouds, a monument to transformation, a testament to the power of planetary processes, a question mark hanging in the solar system, waiting for the next generation of explorers to arrive and, perhaps, to finally unlock its secrets.